In this video, we start discussing chapter 3, elementary functions. Start with section 29. In this chapter, we can see some interesting functions of complex variables such as exponential function, trigonometric functions, logarithmic functions, and inverse of all these things. And first of all, we discuss exponential function, that is omega is equal to f of z, that is equal to e power z. And we can easily find that the components of this f of z is obtained by replacing z is equal to x plus iy. So this can be written as e to the power x times e to the power iy, and equivalently you can write this as e to the power x. This is a real exponential function, and this is also a Euler formula, e raised to iy, that is equal to cos y plus I sin y. So you can replace that quantity by cos y plus I sin y, and consequently you can write this as e to the power x cos y plus e to the power I times e to the power x times sin y. So from this expression you can write this as u of xy plus I times v of xy, which is here this u of xy is nothing but e to the power x cos y, and v of xy is equal to e to the power x sin y. We can easily find that all these functions are continuous, and these functions have partial derivatives of all orders, and those partial derivatives are also continuous, and you can verify that this u and v satisfy CR equations as well in all the convex plane. So this f of z is an example of analytic function, analytic everywhere in the convex plane, hence it is called an example for entire function. Okay, so this e raised to z is also an entire function as well. And all the properties of real exponential functions can be extended to this. That is, if you write this f of e raised to e to the power z1 plus z2 can be written as e power z1 times e power z2. This can be easily verified using this definition itself, e raised to x times e raised to iy, by putting z1 is equal to x1 plus iy1 and z2 as x2 plus iy2. You can easily verify these results. And one important thing is to remember is the derivative of this f dash z, that is d by dz of e power z, that will be the same thing, e power z itself. That is also verified using this definition itself. So these are interesting properties of exponential function, and now you can easily verify that the modulus of this f of z. What is the modulus of f of z? Modulus of f of z is modulus of e power x plus iy, that is equal to modulus of e power x times e power iy. This modulus can be distributed, that is e power x modulus of e power x times modulus of e power iy. But we know that this is the modulus of cos y plus I sin y, and that is nothing but root of cos square y plus sin square y, that is equal to 1, or modulus of this e to the power I times x is always 1, then the modulus is e to the power x, and which is equal to mod e to the power x is same as e to the power x, because e power x is always a non-negative function or positive function. So mod f of z is same as e to the power x. So this is also an interesting property of this exponential function as well. And now this you can write this e power z plus 2 pi I, that can be written as e power z times e power 2 pi I. As this e power 2 pi I is 1, this will give e power z itself, which shows that if we replace this z by z plus 2 pi I, you will get the same e raised to z. Okay, what is the meaning of this statement? The meaning is this e power z or f of z, f of z plus 2 pi I can be considered as, this is nothing but e power z plus 2 pi I. We have seen this is same as e power z, which is equal to f of z. So from this we can say that this f is a periodic function with period 2 pi I. So exponential function is a periodic function with period 2 pi I. Okay, because e power 2 pi I is 1 because of this fact. This is equal to 1. Now what is the argument of this f of z or e power z? What is the argument of f of z? Argument of f of z is we write this is equal to argument of f of z. That is the argument of e power z as well. This is obtained by equating e power z as some modulus times e power I phi, where this phi is the argument of this e power z. But we know that this e power z is same as e power x times e power iy. So this e power x is same as this rho. That's why we call this the modulus of f of z, or modulus of e power z is same as e power x. And the argument of this complex number is this is modulus and this is argument. So argument of this complex number rho times e power I phi is nothing but phi is equal to y, or this can be generalized using 2n pi. This phi will be 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2 etc. That is argument of this e power z is same as y plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2 etc. So this is the argument of this complex function f of z, and this is the modulus of the complex function f of z, okay, or exponential function. And next we will consider a problem to find z equal to x plus iy such that e power z is equal to this e power z is equal to if you find z such that e power z is equal to 1 plus I. This is the question. So this will lead us to another question. What is the inverse of this function e power z? That means if we consider e power z as a function f of z, then we need to find out z such that f of z equal to 1 plus I. That is the meaning of this. So this will give the inverse of this z under this function f. Okay, this can be solved using the equation e power z is equal to 1 plus I. But we know that by solving this we get the value of z. We can use the method of e power x times e power iy. This is the method of finding the real and imaginary parts of complex function e power z. So we can use that method. E power z is equal to 1 plus I implies e power x times e power iy equal to 1 plus iy, 1 plus I. So this we know that 1 plus I can be expressed as or represented as a modulus argument form. We have already seen that problem in our beginning classes. So this can be written as root 2 times this is the modulus of this 1 plus I, and argument of 1 plus I is pi by 4 because of the fact that 1 plus I lies in the first quadrant, and if we consider 1 plus I here, then this angle will be pi by 4 because of tan inverse 1 by 1. So that is equal to pi by 4. So we will get one representation of this 1 plus I as root 2 times e to the power I pi by 4. Okay, so we need to find out x and y such that e raised to x times e raised to iy is equal to root 2 times e to the power I pi by 4. We solve two equations such as e power x is equal to root 2 and e power iy is equal to e to the power I pi by 4. So these are the two equations, and we can also use the fact that this e to the power I pi by 4 can be generalized as e to the power pi by 4 plus 2n pi. We can replace this argument pi by 4 by pi by 4 plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2 etc. We have already discussed this in the starting classes. And from this you can write e raised to x equal to root 2. We can write this x is obtained by taking the logarithm on both sides. So that is log root 2. Log root 2 is same as 1 by 2 times log 2. Because root 2 is 2 to the power 1 by 2, so this x is nothing but 1 by 2 times log 2, and from this equation you can write y is equal to this pi by 4 plus 2n pi, where n varies from 0 plus or minus 1 plus or minus 2, etc. So from this you can write z. What is z? Z is log 2 by 2, that is x, plus I times y. What is y? Y is this thing, pi by 4 plus 2n pi. So this will give z. Okay. So this would lead to define the inverse of a function e power z, or inverse of the exponential function. So we will later we will define this z is nothing but f inverse of. Okay, f inverse of. From this equation you can write this is f inverse of 1 plus I, that is equal to z. From this equation later we will call this f inverse as logarithmic complex logarithmic function. So this is the value of z. So this is one problem you need to go through. This is given as example in section 30. Now we discuss this is given as example in section 29, and next we discuss section 30. In that section we will discuss logarithmic function. So that is the motivation for defining that such a function, logarithmic function, is this problem. And in section 30 we discuss logarithmic function. Logarithmic function. So this function is defined as omega. We define logarithmic function as omega. Omega is equal to this. So we write this as omega is equal to e power omega is equal to z, and we need to find out omega, that is going to be the logarithmic function. If we write omega as log z, then to find out this such a function omega, we write e power omega is equal to z, and we know that this omega can be written as, if omega is equal to u plus iv, then we can write this e power omega is equal to z implies e power u plus I times v is equal to z. Okay, so that implies e power u times e power I v, that is equal to z. Okay, so this z can be written as r times e to the power I phi. Okay, so from this you can write e to the power u is equal to r, and e power I v is equal to e power I phi, or you can write this as e power I times phi plus 2n pi. From these two equations we can write what is u. U is log r, and v is phi plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2, etc. So from this equation you will get omega. Omega is equal to u, that is log r here. This is log r plus this is the real logarithm. Since r is a positive quantity or since the modulus is positive quantity, then log r is defined for every non-zero value. So this is log r plus we write this is I times what is v? V is phi plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2, etc. And we call this omega as log z. Okay, so this is the definition of log z. Log z is equal to log r. Log z is usually written as log of z is equal to L and R. This stands for the real logarithm of r plus I times phi plus 2n pi. N is equal to 0 plus or minus 1 plus or minus 2, etc. So this is the definition of complex logarithm. So complex logarithm of a complex number z, which is equal to r times e raised to I5, can be obtained using this real logarithm of the modulus of r, modulus of z, where this r is a modulus, where r is a mod z, and this phi is the argument of z. Okay. Using the argument of z and modulus of z, you can easily get the value of log z. Okay. So this is the definition of one thing you should remember is this can be defined only for non-zero r. If r is 0, then real logarithm is not defined. Therefore, log z is not defined if modulus of r z is equal to 0. That means log z is defined only when z not equal to 0. So logarithmic function is defined only for non-zero value. Then the domain of from these discussions you can say that the domain of logarithm is nothing but c minus 0. That means log z is a function from c, the set of four complex plane, minus singletons at 0 to again the complex plane. Okay, so this is the domain of definition of logarithmic function. Now you can evaluate, for example, we evaluate logarithm of I as well. What is log I? This log I can be written as logarithm of what is I? I can be written as the modulus 1 times e to the power I pi by 2. Okay, we already discussed how to represent I as a modulus amplitude form. Most generally you can write log z is equal to log I is equal to 1 times, you can just remove this 1, or you have to write 1 times e to the power I pi by 2 plus 2n pi. This is the general form of I. So this can be written as log 1 plus I times pi by 2 plus 2n pi. So this is the values of log I. Okay, where n is equal to 0, plus or minus 1, plus or minus 2, etc. So generally you can write this is, since log 1 is 0, you can write this is I times pi by 2 plus 2n pi, where n varies from 0, plus or minus 1, plus or minus 2, etc. So contrast to real analysis, if you consider the complex logarithm of a complex value, you will get you not only get a single value, but it has more than one values. That means in order to if you choose a complex number I from the complex plane I is here, then try to find out the images of values of log I. What is log I? Log I is obtained from this equation. So these are all imaginary, purely imaginary values. If you put n is equal to 0, you will get I pi by 2. So that will be here. This is I pi by 2. And if you consider n is equal to 1, you will get pi by 2, I times pi by 2 plus 2 pi. So that will be like here, I times pi by 2 plus 2 pi. And if you put n is equal to minus 1, that will be pi by 2 minus 2 pi. So that will be somewhere here, I times pi by 2 minus 2 pi. Okay. So if you choose a single complex number I, log I is not a single value function. Log I will be infinitely many values. Okay, all the values lie inside or lies on the imaginary axis. So log I can be considered as a multi-valued function. That means for a single z, there will be more than one value, or in fact there are infinitely many images for this I. So this I is mapped to all of these values. Log I is here, log I is here, log I is here. There are infinitely many values for this log I. So the log I is not a single valued function. In complex analysis, we usually consider all these single value functions. Even for negative values, contrast to real analysis, you cannot find log of minus 1 in real analysis. If this is a complex number this is a real number r, then what is the meaning of this? The meaning of this is e to the power r is equal to minus 1. So this is not possible in real analysis. Okay, that's why we cannot take logarithm for negative values in real analysis. But in complex analysis, we can easily get logarithms for negative values, because for each negative value we can write minus 1 as 1 times, this is the modulus of minus 1, e to the power I pi. Okay, because the amplitude of this minus 1 is pi. Or you can write more generally, this is log of 1 times e to the power I times pi plus 2n pi. Okay, then by applying the formula for complex logarithm, this will be logarithm of real logarithm of 1 plus I times pi plus 2n pi, where n is equal to 0 plus or minus 1, etc. So this will be log 1 is 0, then this will be I times 2n plus 1 pi. Okay, where n is equal to 0 plus or minus 1, etc. So for even negative values we can define logarithm, complex logarithm. So if we extend our real number system to complex number system, then the function log x can be extended to not only for this negative values, but for every non-zero complex numbers. Okay, so some examples are discussed in section 30 as well. So please go through it.